So welcome everyone to the Lithospheric Tectonics Mantle Dynamics Part 2, as well as the general solid earth sessions for this year's CGU. The Lithospheric Tectonics thing, of course, continues our session from last June, which went really well. We had a lot of great talks. I should introduce myself, sorry. I'm Rustis Klevitz from the University of Toronto, and I'm speaking on behalf of my co-conveners. That's Claire Curry. I don't think Claire's camera's on, and Erkan Gün is also there as well. So I hope you're having a good summer. It's a middle of July day, so attendance might be down a little bit for people as well. You can pretend you're somewhere nice like Banff. I hope you are in a nice pleasant spot. But today we'll listen to 4 talks in our session, followed by a 10-minute break, then the general solid earth session after that. I think many of you have probably attended these talks either at CGU or otherwise, but I'll kind of give you the drill here. We'll have a Q&A after each talk. Please use the Q&A box. This is for the attendees. Use this Q&A box to put in questions, and those could come during the talk if you think of them or after. So type them first, and we'll read out the questions to discuss with the author. Now, if you prefer to speak the question, let me know, and we can open up the microphone and allow you to speak as well. I was just going to say, one of the great things about CGU is it's a nice, small, intimate meeting. So feel free. This is a friendly and open meeting. So especially questions from students would be really great to get here. So again, students, kind of feel free to jump in at the end if you have any questions. So on to this session, I won't do a long preamble. Erkan gave a really nice intro last time. I'll just say we really designed the session to bring together talks on both tectonics of the lithosphere as well as mantle convection, essentially trying to unravel that enigma of plate tectonics, where mantle may be a thermal engine to drive lithospheric motion and stress. And then the lithosphere manifests that to give us this intriguing tectonic behavior. I think we can take some pride. Canadian geoscience is particularly strong in geodynamics and tectonics and mantle convection. And it was great to see some excellent talks last session. And we've got a great lineup here today. So sit back and enjoy these. I apologize, I have renovations going on. I don't know if people can hear bumping there next door. So on to our first speaker, and this is Kristina Kublik, with co-authors Claire Curry and Graham Pearson, all from the University of Alberta. And Kristina will be talking about modeling the topographic response to craton formation by lateral accretion. So Kristina, we're kind of a minute ahead here, but why don't you share your screen and get going when you're ready. Looks good.
Okay, I'll just go up to the beginning. I should just stop this for a bit. I'm giving the end away too soon. Okay, sorry about that.
It's okay, no problem.
Okay, so everything's working all right?
Yep, looks perfect.
Okay. Well, thank you for hosting the online session today. I'm working with Claire Curry and Graham Pearson on a numerical modeling project at the University of Alberta that's investigating topographic subsidence following the lateral accretion of cratons. Cratonic basins contain some of the largest resource deposits in the world, but how they're formed is still not well understood. The SOPEL code we use models lithosphere geodynamics, and we're hoping to find a set of mechanical and thermal parameters that enable basin subsidence over a thick, stable cratonic route. SOPEL was developed by the Dalhousie Geodynamics Group in Halifax, and I run these models on Compute Canada's CEDAR cluster. And before I begin, I'd like to acknowledge the Diamond Exploration and Research Training School and NSERC for their financial support on this project. I'll start by giving you an overview of what my models do, and then I'll show you how different parameters can have a significant impact on the final geometries. Okay, so this is the initial setup. My model domain is 2,400 kilometers wide and 660 kilometers deep. All this white material is sublithospheric mantle. There's a 20-kilometer thick upper crust in yellow and a 20-kilometer thick lower crust in green. And the gray is the 110-kilometer thick mantle lithosphere. The darker gray portion represents depleted mantle material, similar to what you would find in Archean cratons. This is loosely based off of the mantle plume model for craton formation, where this lithosphere is the depleted residue left behind after melting. My models are not trying to justify one craton formation theory over another. All I'm doing is looking at a small parameter space that may or may not encourage basin subsidence. Partial melting in the mantle has stripped the cratonic material of water and incompatible elements such as calcium and aluminum. When this happens, the heavy mineral garnet won't be as abundant, contributing to lower density in the residual material. The values chosen for these models fall within the range described by Pearson and Wittig. Drier rocks have a much stronger rheology, and for the purposes of our model, we assume that the craton is 3 times stronger than the surrounding lithosphere. And this is based on results by Wang and others. For each of the plots you'll see, this number represents elapsed time from the start of the model. The initial thermal conditions are defined at the bottom and the side boundaries, and we specify the temperature and heat flow at each surface. There's a short model spin-up phase to allow the thermal conditions to propagate throughout the model using the values assigned for conductivity for each material. The isotherms here are in 300-degree increments, and the temperature doesn't change as quickly once we're in the mantle adiabat, and that's why there's a large gap between these last 2 isotherms. The spin-up phase also gives the material a chance to reach isostatic equilibrium, and because of the different densities in the mantle lithosphere, there's been a small amount of uplift. This plot shows topography, and this light gray line is 1.5 kilometers above the original baseline. After 1 million years of horizontal compression at 1 centimeter per year, there starts to be a little bit of shortening occurring in the areas with weaker lithosphere. And there's a little bit of deformation occurring at surface. After 25 million years, deformation is more extreme. We see a little bit of shortening in the depleted region, but most of the shortening is accommodated within the weaker lithosphere. At the end of the compression phase, which I've defined to be 50 million years, wild topography has developed, and there's noticeable shortening and thickening even in the depleted central cratonic region. There's some surface deformation above the craton, but it seems that most of the shortening has been accommodated in the side with the weaker lithosphere. Okay, so now we're getting to the part that deals with my actual research question. After craton thickening, does widespread subsidence occur? I'm going to scroll through the next several slides quickly, and I want you to watch how topography evolves. Use the 0 and the 1.5 kilometer lines to help guide your eye, and each time step will be 50 million years. I ran this model for 500 million years after the end of the compression phase, and it's clear that subsidence slows a little bit with time. I'm going to go through these backwards now, and you'll see how there's quicker subsidence as we get closer to the 50 million year mark. With the largest jump happening between these 2 frames, right at the beginning. I'll go through this once more, and this time look at the area above the weaker lithosphere. Very quickly, the extreme topography evens out, and it almost looks like the peaks are migrating outwards. So between the lithosphere and the surface topography, there's a lot going on. And I should point out that surface processes like erosion and sedimentation are not included in the model. So all of the subsidence we've seen so far is the result of lithosphere geodynamics. I'm going to jump back to this frame because the environment that exists at the end of the compression phase sets the stage for what happens over the next 500 million years. I spent some time investigating how different parameters can change the geometries at the end of the compression phase, and I'm going to show you just a handful of those results. I'll first shift this figure to the side so we can compare a few models at once. In the second plot now, everything is the same except for the crust is weaker. The crust thickens in a localized area, which concentrates the shortening within the non-cratonic lithosphere. And you can see that there's less deformation over the central plateau. And this is even more extreme when the crust is weakened further. This is a 300 to 400 kilometer wide mountain that is over 4 kilometers high. Moving forward, this model in the middle is the reference experiment, and I'll use it to compare all the other scenarios. And here are two examples of crustal rheologies that are 10 times stronger and 10 times weaker than the reference. And we can think of the stronger scenario as having a dry mafic crust, which is much stronger than a well-hydrated crust of felsic composition. And these general relationships have been discussed in a few different studies. These two plots quantify how crustal strength influences the deformation of the craton. That's this dark gray portion of the lithosphere. The x-axis is a log scale with increasing crustal strength relative to the reference. We've got the reference here at 1, and over here is the 10 times stronger end member, and on the left is the 10 times weaker end member. The y-axis is the shortening factor beta, which is the ratio of the final and initial width. The blue lines show conditions after 25 million years of shortening, and the red line is after 50 million years. So there's a very clear trend that stronger crusts help shorten the craton. And when the crust is strong, shortening occurs continuously over 50 million years. But when the crust is weak, there's hardly any additional shortening after the first 25 million years. This plot on the right shows craton thickening, and as expected, there's more thickening in models that have had more craton shortening. And this is an important result to note, because a thick cratonic root that extends down to about 200 kilometers depth is what we see in cratons that are preserved today. The blue line is at 200 kilometers depth, and in this model, the stronger crust helps the lithosphere thicken into something that may resemble a cratonic root. Okay, back to the reference slide. In this model, radioactive heat production in the crust is similar to what you would expect in the present day. For this model, we've doubled heat production to simulate Archean to Proterozoic conditions, where heat-producing elements are more abundant. The resulting topography is very similar to the weak crust model that we just saw. When I overlay those two models, the topography is clearly very similar. The blue curve here is for the model on the right, on this slide, where the crust is weaker from a thermal perspective. And this red curve is from the model on the previous slide, where the crust was weak from a mechanical perspective. When we make the crust hotter, this blue line, the rheologies are more viscous, so even though the crust is weak, it's not necessarily brittle. For the red curve, frictional plastic deformation dominates, and topography is more jagged and higher. Okay, so back to the reference model. Remember that the craton is stronger than the surrounding lithosphere and less dense. But what happens if we increase the density? When the mantle lithosphere has uniform density, there's no uplift. There's a little more shortening in the depleted region compared to when there's a density contrast. But because this area is still 3 times as strong as the rest of the lithosphere, it's able to resist deformation a bit. On the other hand, decreasing the density results in the uplift of a tall plateau over 200 kilometers high that is very resistant to deformation. This time, the x-axis shows increasing cratonic density on a linear scale. We can see that for all densities, most of the shortening occurs within the first 25 million years, because there's very little separation between the 25 million year line and the red 50 million year line. When the craton has the same density as the surrounding lithosphere, it's more easily deformed and continues to shorten for the entire 50 million years. And this denser model also sees more cratonic thickening. For reference, here is this line at 200 kilometers depth. So this model is able to build a thick craton similar to what we see preserved today. These next models will show the effect of some added heterogeneity. Here is a small block of eclogite that's added to the base of the lower crust in the center of the model. It's subtle, but there's a little extra shortening that occurs within this depleted region, and the denser material creates a negative topographic feature. The red block here represents a pocket of metasomatized mantle. This creates a small zone of weakness that facilitates some shortening in the craton. This area has all the same mechanical properties as the rest of the lithosphere mantle, and the only difference is that there are more radioactive elements in this small block compared to the rest of the mantle. So this is a purely thermal effect on the geodynamics. This is the value I'm using for radiogenic heat production for this red area, and for the rest of the mantle, A is equal to 0. What I find interesting is that these two heterogeneities have a similar effect on the subsurface, even though their surface expression is in opposite directions. Both of these models deform the craton more than the reference experiment, but it isn't as drastic as we've seen in some of the other models. Here is the eclogite model that has slightly more shortening than the reference, and here's the metasomatized model with a little bit more. As expected, the craton thickens as it shortens. But when compared to the reference model, the eclogite in the lower crust does not result in a thicker lithosphere. However, thermal heterogeneity caused by metasomatism does enhance cratonic thickening. So that's a broad picture of the first stage of my experiments. The main point I wanted to show is that even with this relatively simple setup, there's a ton of possible variations that can have a major impact on the results. In general, in this pure shear tectonic setting, cratonic thickening is enhanced if the crust is strong, either mechanically or thermally. There's less of a density contrast within the lithospheric mantle, or if there's some kind of heterogeneity that can localize the shortening. And metasomatism in particular can effectively increase craton thickness. My next step is to rigorously examine how different parameters impact basin formation. That will include looking at the effects of surface erosion and sediment loading on wide-scale subsidence. My goal is to find models with subsidence rates comparable to those estimated in Archean and Neoproterozoic basins, like the Witwatersrand in South Africa and the Athabasca Basin in northern Alberta and Saskatchewan. Thank you all for your attention, and I would be happy to answer any questions now.
Great, thanks, Kristina. Really interesting stuff there. Okay, we have a couple questions already posted. Other participants, feel free to enter some as well. So first one here we have, Kaylin Wang asks, the model is purely symmetric. What causes the asymmetry in the reference model results?
Are you referring to, just let me go back here. Yeah, kind of these little blips here. Is that the asymmetry they're talking about?
Why don't you, yeah, sure. Why don't you answer based on that?
Okay. So this is a bit of a surface. It's a bit of a numerical instability that's occurring at the surface. And after running some of these models, there's a small parameter called the surface stabilizer that I need to include, which will smooth out the topography there. But I guess the short answer is that it's a numerical instability situation, not like a real world result. And so like the big picture though, is that the topography is symmetrical.
Okay. Actually, Kaylin, he just elaborated a little bit that not the topography, but more so the flow pattern in the mantle. So the dark gray region. I mean, less so in this plot, but maybe, are there other plots where it shows some asymmetry in kind of the sublithospheric flow?
Would it have been in that little video that I showed, like this part?
Yeah, probably.
Okay. So I haven't actually thought about that, or I didn't notice that there was substantial asymmetry happening in the flow. So I don't have a good answer to that question. Sorry.
That's okay. All of these are just, it's feedback to think about. Kaylin actually had a second question here too. Or actually, maybe I'll start with Phil's and come back to Kaylin's. So Phil McCausland asked, well, he said, thanks, Kristina, for your talk. Nice work. Does starting the crust surface at 0 kilometers or different elevations make a difference? The elevation is tied to surface to effective sea level. That's a question. This freeboard would then matter for future consideration of erosion. So kind of the starting level for the topography.
Oh, that's also something I didn't look at. I did run a lot more models where I varied the density differently. And so then after your like spin up phase where isostasy equilibrated, then I had like a slightly different starting point for, say, right here, like right here. But as far as starting at 0, I believe that's just the model default, and I never really thought of changing that, because if you start with your surface at 2 kilometers above, then just the whole system shifted. So I didn't really think that would have too much of an effect on that, and I didn't consider it, but it would be worth looking into.
Okay, cool. Kaylin has another question, but maybe we'll answer that offline. So Kristina, you'll be able to see that, I think, and you could type an answer to that. So sure. Thanks. Excellent job. So I think we'll move on here.
Thank you.
Our next speaker then is PhD student Erkan Gün. He's from the University of Toronto. So his co-authors are myself, Oz Ghosh, and Gültekin Topaz. Oz and Gültekin are from ITU. And Erkan's going to talk to us about something called the subduction pulley. So Erkan, you want to pull your screen up and share it?
Oh, thanks, Russ. Share my screen. Does it look good?
Yep, looks good.
Okay. Hello, everyone. My name is Erkan. I'm a PhD candidate at the Department of Earth Sciences of the University of Toronto. And today I will be presenting part of my PhD work that focuses on subduction zone processes and the pre-collisional extension of microcontinents. Before I go further, I just want to give you a brief intro what I'm going to talk today. What you see here on this map is actually these gray shaded areas show orogenic baths, which are actually formerly subduction zones and convergent plate boundaries, and also active subduction zones around the Pacific region. And these red shaded areas show mostly oceanic terrains, but there are also some coastal ones too. So why it is important to see this picture? Because all these terrains are anomalously high, take coastal regions inside of the ocean lithosphere. So basically, ocean lithosphere is not a homogeneous plate. And it carries all these terrains to subduction zones, where they are going to sink into the astronosphere, or they are going to upgrade to the overriding plate, creating all these orogenic baths, such as North American Cordillera or Alpine Himalayan beds. So this is also an important feature of the crustal growth. So today I will be focusing more on Alpine Eastern Mediterranean region later. So by definition, terrains are allochthonous fault-bounded rocks with a different geologic history than that of adjacent rockiness. So terrains can be continental, such as microcontinents, island arcs, and seamounts, or oceanic, such as oceanic plateaus, again, seamounts or seismic ridges. Again, today I will be focusing more continental terrains. So here is a map of tectonic map of the Eastern Mediterranean region. So basically what you see here with different colors are, they're all different terrains. They came together with the end of the subduction zone processes. For example, all these terrains are bounded by suture zones, and they are actually graveyards of the former oceans. In this case, Tethys Ocean subducted along this Ankara-Erzincan suture and Bitlis-Zagros suture. So another important feature of the subduction zones are extensional tectonics. Normally, so it's been suggested that, and also very well recognized that the backarc regions of the subduction zone can extend due to the slab retreat. And for example, if a continental terrain drifts to the subduction zone, it cannot usually sink into the asthenosphere due to its buoyancy, and it upgrades to the overriding plate. And after that, being in the location of in the backarc region, it can extend due to the slab retreat, causing post-collisional terrain exhumation or extension. Another mechanism that's been suggested for this kind of extension is the gravitational collapse. Basically, because of the continental collision of the continental block with the overriding plate, it shortens and thickens its lithosphere, and then after that, it cannot carry by its own weight, and it collapses. So, but what about subducting side of the subduction system? So we don't know anything about this part of the formation. So this is very well recognized, post-collisional exhumation extension, but little to no recognition of this part of the deformation system. But there are some intriguing cases from Alpine Eastern Mediterranean region, specifically from the Sesya zone from the Western Alps and the Eastern Akdağ region from the Eastern Anatolia. These cases are important because they show an exhumation timing prior to collision. For example, Sesya zone, it was a ribbon-like macrocontinental block was traveling or drifting to the Adria-Europe subduction zone 85 million years ago. So, but the exhumation and extension of the rocks happened 80 to 60 million years ago. And what we know that collision on this subduction zone was 50 million years ago. So it is clearly that doesn't fit the previously suggested post-collisional extension idea, because extension is prior to collision here. And the same thing for the Akdağ region in the Eastern Anatolia. But we know that this exhumation of the mid to lower crustal rocks of this Akdağ region exhumed to the surface or subsurface levels at 71 million years ago. But we know that collision along the İzmir-Ankara-Erzincan suture zone happened 50 million years ago. So we have these two cases that suggest that this extension is also happening prior to collision, but we don't know how. And because of that, to understand better what is happening in these regions, we created this numerical modeling setup. So basically in this setup, what you see is a subduction zone. There's one oceanic lithosphere subducting and carrying a microcontinental block within to the subduction zone. So we tested different size microcontinents, starting from 120 kilometer to 600 kilometer. And we also tested different convergence rate velocities, such as from 0 centimeter per year to 4 centimeter per year. So if it is 0 centimeter per year, it means that the only plate driving force in the system is the slab pull. But if there is a 2 and 4 centimeter per year impulse velocity, we apply this velocity from the right side of the box, and it is mimicking the reach push effect in the system. So here are some of the results of this experiment. On the top half of the slide, you see some frames from the experiment one. In this experiment, we use a small microcontinent, which has only 120 kilometer width. And it is in this inset shows the initial state of the microcontinent. In this left frame, you see the after 5.5 million year, and when this microcontinent reaches the subduction zone and starts colliding with the overriding plate. But on the right side, you see after the collision and the slap breaks off, that happens 7.1 million year ago. So to understand the pre-collisional deformational patterns, so we tracked some of rocks from mostly from the lower crustal rocks of this microcontinent. So you see this point here. So let's focus on this pink one. So we track their pressure, temperature, evolution path during the evolution of the models, and we plot them on the right side here. So as you can see, initially these rocks are, for example, pink one, almost under 8 kilobar lithostatic pressure, but with the development of the model, this pressure drops, which means that this lithosphere is extending and thinning, and because of that, lithostatic pressure is decreasing. And also it means that also there is extension happening prior to collision. Also, you can see from the graph here that the width of the microcontinent is longer when it arrives to the subduction zone. And the bottom half of the slide, you see similar experiment, but the microcontinent width is now 300 kilometers. So it's maybe more obvious here to see the extension in the microcontinent. And again, on the right side, you see the exhumation of the tracked rock packages. So these are the same experiments, but the 450 and 600 kilometer wide microcontinents. And we see the same patterns again. But the only difference is that if you see the summary of this experiments, so here we plot this beta factor, which is essentially the extension factor here. If this number is high, it means that there is more extension. If it is low, this extension is also low too. We plot this beta factors versus microcontinent width. And you can see that there is a trend there. So when the microcontinent width is increasing, there is an increase in the extension magnitudes. And also, there is another important thing to consider here is the convergence velocities. If there is no convergence, imposed convergence velocity in the system, which means that slab pull is the only acting force in the system as a plate driving force, we see the highest extension magnitudes. But if there is a imposed velocity such as ridge push in the system, this extension factors decreases significantly. So if you go back to the geology, here you see a map of the Sessia zone from the Western Alps. So the thing to consider here is this eclogitic mica schists, which are higher grade metamorphic rocks. They exhume to the surface levels along this detachment faults. We also compare our plotted or calculated pressure temperature data from one of our models, which is experiment 3, against geological petrological data. These references are here, and to see if there is similarities. As you can see, also that paths are following a similar trend. And also for the Eastern Anatolia case, so you see the same feature here. This higher grade metamorphic rocks of the Akdağ region exhume to the surface levels along these detachment faults. And we also know that one of the co-authors worked in this region and dated all these rocks. We know that this exhumation of these rocks happened prior to collision along the Izmir-Ankara-Erzincan suture zone. So to simplify what was happening there, we came up with this mechanical analog. We call it the subduction pulley. So in this mechanical analog, what you see is the slab, subducting oceanic slab considered as a weight in the mechanical system. And also the trench is represented by a pulley, which changes the direction of the tensile stress that originated from the slab from vertical to subvertical levels, so direction to the horizontal direction. And the microcontinent is represented by a dashboard, and the strong oceanic lithosphere represented by a string. So when this weight goes down or slab sinks into the asthenosphere, it pulls the upper horizontal extent, and with the help of this pulley analogy, and the microcontinent becomes the focus of the tensile stress and extends because it has a lower lithospheric strength compared to oceanic lithosphere. It's been also suggested that this oceanic lithosphere, if it is older than 10 million years, so it should resist the tensile stress. But we also know that this continental areas, they are the preferential places for, let's say, lithospheric rifting. So the results of this study has been published in Nature Geoscience recently. If you would like to see the details, please check our paper. So also I'm going to play a short animation here to show you what was happening in the subduction pulley system. And this is one of our experiments, which is experiment 5. We juxtapose also our mechanical analog at some frames. Let me play this. So when the slab pulls start to act and start to pull the upper extent of the ocean lithosphere, this microcontinent start to drift to the subduction zone. But with the movement and the tensile stress, it can not resist the tensile stress as much as lithosphere, oceanic lithosphere does, and it extends. And then after that, subduction process continues, and this microcontinent collides with the overriding plate, and eventually the slab breaks and this microcontinent applies to the overriding plate. And that will be all. Thanks for listening. And I'm happy to answer your questions.
Thanks, Erkan. Yes, as Erkan says, if there's any questions, type them in the box. Erkan will answer. I give everyone permission to ask difficult questions of Erkan as my grad student here. He can answer.
Sure.
Maybe I'll start off with kind of a leading thing for some discussion. So if this is, seems like an interesting process here, this pre-extension prior to collision, why don't we see this everywhere? Why has it taken so long to recognize something like this?
What I think, actually not just me, so we think is, we think that this post-collisional processes or metamorphism or deformation, they overprint this pre-collisional episode of the deformation. And because when this microcontinent arrives to the subduction zone, such as here, and also it subducts a little bit, and these are really high pressure conditions and high pressure and high temperature conditions, probably it overprints the previous deformation episodes, such as this pre-collisional, what we suggested. And I think it causes some misinterpretation of the geological data. So what we think that is important to recognize, this could also happen, and there are some geologic examples, as very clearly says in this literature, Sessia, and also we are very confident of this case of the East Anatolia because our co-authors worked there and dated these rocks, and we are pretty sure that this is happening prior to the collision, and we are hoping that it will be recognized after maybe seeing this mechanism.
Okay, cool. Thanks, Erkan. Claire, you want to unmute and ask your question?
Sure, hopefully that's working. Thank you very much, Erkan. Very interesting work and a great talk. I was wondering if you could say a few words about the structure of the continent that you're using. Like, what is the crustal thickness and the rheologies, and did you vary those at all? Yeah.
Yeah, so crustal thickness is 30 kilometers here, and the mantle lithosphere is 70 kilometers. It should be considered as a previously rifted microcontinental block from a maybe larger continent. That's why it is a little bit maybe thinner than regular continents.
I guess,
So-
what rheology are you using in the continental crust, and does that affect
crust
the...
is the continental crust is represented by wet quartzite,
Okay.
and also Mantle lithosphere was wet ahamdonite.
Did you
also
vary
we
those
use-
at all, or
Sorry?
did you vary those at all?
Yeah, we tested different Mantle lithosphere rheologies, and they gave all the same results. We didn't. Also, if you check our paper, there is a supplementary file, and we also add this extra tested Mantle lithosphere lithologies if there is an effect, and we couldn't find. There is only one effect that we significantly realized that affecting it is the impulse convergence velocity. So if you increase the impulse convergence velocity at, let's say, 8 to 10 centimeter per year, in addition to the slab pull force, you can effectively shut off the pre-collisional extension.
Okay, great. Thank you very much.
Thanks, Claire.
Okay, thanks. We can, Sam Butler has a question. We'll squeeze in. Again, apologies, this is going to drive you crazy, this noise here. When the slab reaches the bottom boundary of this simulation domain, is the tensile stress in the slab reduced? I guess, and then will there be differences with a deeper simulation domain? So
I don't think so. Maybe, but we didn't test that much because when it reaches to the to the bottom of the bus, already this microcontent is reaching to the subduction zone. But we had some other models that we placed this microcontinent so far from the trench, and in this experiment, it reaches to the subduction. The bottom of the model box, but still we see the pre-collisional extension. It may reduce maybe the magnitude of pre-collisional extension, but I didn't pay attention. That is a good question. Maybe I should check this.
Okay, again, we'll try to squeeze. Phil has a question here. Says, nice work, Erkan. This is modeled as an orthogonal closure in 2D. What's the effect of along strike motion on the microcontinent as it's about to accrete? Also, how far away, how much time in million years does the pulley start to take effect prior to microcontinent collision?
Yeah, we didn't test 3D setup yet. So I think you're asking 3D effects, the possible 3D effects on this pre-collisional extension. This is actually one of the next steps that we are going to test. So I don't know yet. So it may increase the amount of the pre-collisional extension because of the lateral slab pull forcing might increase, but on the other hand, it can decrease too. So we don't know yet. So this is a good question, and I'm going to test this with this 3D model soon. The code that I'm using doesn't have 3D capabilities, but I'm going to switch another code and test this idea with that code.
Okay, I'm going to cut you off there, Erkan, because it's 2:15, okay, and we'll move on. Phil had another part of his question you could answer online, and there's another question there by Li Zhen Cheng, if you want to answer that.
Okay, I'll answer that in the chat.
Okay, next up is Xiaowen Liu from the University of Alberta. Xiaowen, if you want to start sharing your screen once Erkan gets off. Co-author is Claire Curry, also from University of Alberta. And Xiaowen, I can read the title slide, is going to talk about driving forces of the Sierras Pampeanas, if I pronounce that right, during Pampean flat slab subduction. Go ahead, Xiaowen. Thanks.
Okay, thank you, Russ. Hi, everyone. The topic of my today's talk is driving forces of the Sierra Pampeanas during Pampean flat slab subduction. I'll start my talk with this simple topographic map of South America. To the west of South America, there's a long subduction zone. Along the Peru-Chile Trench, the Nazca Plate and a part of Antarctic Plate are subducting beneath the South American Plate. The geometry of the subducting slab varies from location to location. This includes 3 segments of flat slab subduction: the Bucaramanga flat slab in Colombia, Peruvian flat slab, and the Pampean flat slab in central Chile. The convergence due to the convergent margin leads to the shortening of the west margin of South America and the formation of the longest continental mountain range, the Andes. One of the interesting area here is here. So in the central Chile, there's a high topography in the Andes where the typical volcanic arc is at. And to the east of it, where in the foreland region, there is also a high surface elevation, which is the Sierra Pampeanas. So my research will focus on this area. The Sierra Pampeanas coincides with the Pampean flat slab, and my research will look at how the Pampean flat slab subduction will influence on the Sierra Pampeanas. Okay, go back a bit. So what is flat slab subduction? In a normal subduction zone, the descending slab subducting steeply into the mantle due to the dense oceanic plate. And the descending angle normally ranges between 30 to 90 degrees. And due to the presence of the mantle wedge, dehydration from the slab causes partial melting in the mantle wedge, which form a volcanic arc in the continent. However, in some of the subduction zones, there's no active volcanism, and the intra-slab seismicity show a different geometry, a flat slab. This is when the subducting plate unbends in the upper mantle to form a flat geometry beneath the overlying plate. And flat slab subduction occurs in 10% of modern subduction zones. And the mechanisms of formation of flat slab is complex, and multiple researchers have studied why flat slab occurs at certain regions. And the causes of flat slabs are attributed mainly to the three factors. The first one is a buoyant oceanic plate. It's either due to a young age or subducting of a low density aseismic ridge. For example, the Nazca Ridge in the Peruvian subduction zone and the Juan Fernandez Ridge in the Pampean flat slab subduction. The second factor is a trenchward motion of the continental plate. So when the continent is overriding the subducting slab, it tends to form a flat geometry. And the third factor is low pressure in the mantle wedge. So this increases the suction force to pull the slab up into a flat geometry. Next, I will zoom in to the Pampean region. So in this map that I created, so the red triangle shows where the active volcanism is at. And in between, where there's no active volcanism, is a Pampean flat slab. The subduction direction is roughly parallel to the AA prime. And on the right-hand side, the figure shows the cross-section of AA prime along with the surface topography. Pampean flat slab at its current latitude started to form the flat geometry around 11 to 12 million years ago. And the Pampean flat slab correlates spatially with the subduction of the Juan Fernandez Ridge, which is believed to be one of the reasons caused the Pampean flat subduction. And this region also correlates with the Sierra Pampeanas. The Sierra Pampeanas is a crustal scale shortening and uplift that is further from the convergent margin in the foreland region. And this area also correlates with, has a history of terrain accretions in the late Proterozoic to early Paleozoic, and also episodes of extensional events in the late Paleozoic and Mesozoic. There's some main terrains here, the Chilean, Cuyanian, Fermatina, Pampean, and Corbado terrains. And to the east of these terrains is the Rio de la Plata Craton. And the terrain boundaries are based on the reference from these three papers. My current research is focused on to examine the mechanisms that causes a basement block uplift in the Sierra Pampeanas. And here I show two of the hypotheses. The first one is the increased stress at the convergent plate margin due to the subduction of the flat slab. And the second is the presence of a pre-existing weak zone, which here is caused by the terrain suture zones or the rift zones. Okay, in my research, I'm using 2D upper mantle scale thermomechanical models. The models use finite element code SOPEL. And my model is based on the Pampean flat subduction. All the materials in the model have viscous plastic rheology. This figure shows the initial model setup. My model domain is 1,800 kilometers in width and 1,200 kilometers in depth. On the left-hand side is a 80 kilometer thick oceanic plate, which corresponding to the 14 million year old Nazca plate. And there's a 1,200 kilometer wide oceanic ridge to represent the subducting Juan Fernandez ridge. And on the right-hand side is the continental plate. It includes a 120 kilometers thick lithosphere in the normal part and 200 kilometers thick in the craton part. In the continental part, I also added 5 narrow blocks of the weak zones, and the location is corresponding to the terrain boundaries. And for the weak zones, I use a low frictional angle to represent the broken zones. The convergence rate between the Nazca plate and the South America plate is 8 centimeters per year based on plate reconstruction. And the plate velocity of the oceanic plate and the continental plate is based on a hotspot reference frame. Our model runs on the continent reference, which means the velocity of the continent will be added to other boundaries in the opposite direction. And on the right-hand side is the geotherm of the oceanic plate and the continental plate. Our model runs for 20 million years, but in this talk, I will only show the initial 12 million years, which kind of represents the subduction of the Pampean flat slab at its current location from 12 million years ago to present day. Next, I will show some of my preliminary results. This model, in this figure, the bottom figure shows the model domain, and the top figure shows how the surface uplift changes as the model runs. And the first model has a uniform continent, and there is no wake zone in the continental plate. The model run from, I will show 0 to 12 million years, and this is a video, so each frame is 0.5 million years. As we can see here, the model starts with a steep angle subduction, and at 0 MA, the oceanic plateau just enters the trench. Okay, I will play this video. As the oceanic plateau enters the subduction zone, the buoyancy force dominant, and also along with the high trenchward motion of the continent, it creates a flat slab. I will play again. If we focus on the surface uplift, we can see that there's a dynamic uplift above the oceanic plateau. Now I will zoom into this red rectangular region to look at the stress field of this model. So the upper figure shows the horizontal divertoric stress, and the bottom figure shows the maximum shear stress. And you see the black dots, that represents oceanic moho. We can see as the plateau enters the subduction zone, the stresses in the continental crust increases, and the stresses is kind of uniform across the whole continental crust. And I play again. If we look at the Mantle lithosphere, there's not much stress in the Mantle lithosphere. This shows that the compression of the continent by the flat slab is due to the unloading at the trench, instead of the stress transfer from the basal shear traction. Another thing I want to point here is we look at the horizontal divertoric stress. On the surface, there's an extension above the plateau, which corresponding to the dynamic uplift at the surface above the plateau due to the buoyancy of the plateau. In the second model, I added the 5 blocks of the wake zones here. In this model, the wake zone only in the upper crust. When I play this model, during the development of the flat slab, we can see there's a little bit deformation at the suture zones that is close to the craton boundary. Other than that, there's no obvious deformation occurred in this model. And if I compare the 12 million years, which at the end of the model compare with the actual surface topography, there's not a lot of similarities with our model results and surface topography. And in the second model, weak zones cut through both upper crust and lower crust. And in this model, as we can see, when the oceanic plateau enters, the stresses in the continent increases and there's shortening and uplift occurred within the weak zones or the suture zones. And if I compare this frame with the actual surface topography here, from our model results, the surface uplift kind of correlates well with the actual surface topographies. And this is the third model. I extend the weak zone into the Mantle lithosphere. As the subduction of the oceanic plateau, there's a huge amount of shortening and surface uplift happens. Due to the great amount of shortening, within the 12 million years of model time, there's no flat slab created. Based on the model results of these three sets of models, the weak zone seems need to be cut through the upper crust and lower crust to allow like decent deformation to happen. Okay, next, I will go back to the model which is better represents the Sierra Pampeanas. Just to remind you, this model, the weak zone cut through upper crust and lower crust. And now I will look at the stress field of this model. As what I showed before, when the oceanic plateau enters the trench, the stresses in the continental crust increases. And due to the presence of the weak zones, the stress releases at the weak zones and then causes deformation. I will play again. And you can see because of the weak zone didn't go through into the Mantle lithosphere, there's a really high stress at the bottom or the very top of the Mantle lithosphere to hold the stress from breaking and have decent amount of deformation here. And one question is, does all the deformation occur at the same time at the 5 different suture zones? So here I have plotted the string rate field of this model. Play this. During the development of the flat slab, we can see at the suture zones, the strain rate increases once the compression increases. And I'll play again. From this video, it seems the strain rate increase altogether at all the 5 suture zones. And to have a better look at the magnitude of the strain rate of the weak zones, I have plotted the strain rate in the lower crust from 600 kilometers to 1300 kilometers. And here, if we look, when the subduction happens, all the 5 suture zones start to increase the strain rate. And then towards to the end of the model, it seems the strain rate that nears the craton boundary is higher than the ones like close to the trench. And one of the reasons I was thinking is maybe because when the plateau comes in, due to the buoyancy of the plateau, there's an uplift above the plateau region, and which emerges with the deformation of these 3 suture zones. But I'm still currently working on this part and trying to find a good explanation of this phenomenon. I would also, if anyone has suggestions and comments, I would like to take them. Okay, at last, I will show some extra models. This model shows a uniform long wake zone. So there's no small blocks. So the whole thing is a wake parts. It's in the upper crust and lower crust. When I play this model, we can see at the beginning, it seems the deformation starts to happen in the center and the 2 edges of the long uniform wake zone. Play again. But on the left side of the wake zone, because of the uplift as well, it kind of doesn't show that obvious as like the deformation on the right-hand side. But based on this model, we can see before when there's certain suture zones, it can localize the deformation. But when we have a long uniform one, it seems only it happens in the center and the two edges. And the next models I want to show is a normal angle subduction. So this is the reference model, like that better represents the Sierra Pampeanas. On the left side, it has the same properties of the weak suture zones, but the subduction is a steep angle subduction. With the similarity, with the same weak zones, a normal angle subduction does not create any shortening or uplift. So this means the inboard deformation, it needs a presence of a flat slab to increase the compression or the stress in the continent, and a pre-existing weak zone to trigger the inboard deformation. In summary, based on my preliminary results, the basement block uplifts of the Sierra Pampeanas are induced by the increased stress in the continental crust due to the Pampean flat subduction. And the high compression in the continental crust resulted from the flat slab is through unloading instead of basal shear traction. And pre-existing weak zones such as the terrain, suture zones, and reef zones are reactivated during the high compression during flat slab subduction. And the deformation is localized within the weak zones and with surface uplift concentrated at the terrain boundaries. Okay, that's my talk. Thank you. Now I'd like to take any comments and questions.
Okay, thanks, Xiaowen. Russ just had to step out for a couple of minutes, so I'm just filling in. So I think we've got about 2 or 3 minutes for questions if anyone wants to type something quickly or. Maybe I'll ask a general one. You sort of, oh, actually, can Kellen speak? I'd say yes, but I don't know how to open the microphone. Okay.
Yeah, a button came up. Yeah, okay. Well, thank you. Very beautiful work. Yeah, my question is for the last slide, you showed the normal dipping subduction. Yeah, normal angle and flat slab. Is the normal angle subduction produced with a different set of boundary conditions? How did you make it normal?
Okay, in the early of my talk, like to create a flat slab, like there's 3 factors. One is the buoyancy of this plateau subducting. It kind of pull the slab up. Another one is a super high continental trenchward motion of the continent. Because our model is a continental reference, so the velocity of the continent is actually added to like other boundaries.
I understand that part.
Yeah. So in the normal subduction, the boundary condition is the same, just like we don't have a super fast trenchward motion of the continent, and also I get rid of the buoyant oceanic plateau.
I see. Okay, thank you.
Okay, according to my clock, we're actually right at 35 minutes past the hour. So I think we do have to change speakers, but okay. A question has come in from Phil, but I think you can answer that by typing.
Yeah, sure.
Okay.
I'll stop sharing.
Okay. I think then we're on to the last talk of the session by Tasca Santimano. Hopefully I'm pronouncing that correctly.
Okay, I think I'm sharing my screen.
Yeah, I think it's just coming up right now. Yes, looks good. Okay, so Tasca is going to present on, I guess, more scars in the lithosphere. So go ahead.
Yeah. Okay, well, thank you to the organizers and for organizing the session and the conference. Today, I will be talking about the influence of the lithospheric mantle scars and also rheology, so an interplay between the structural heterogeneities in the deep lithosphere and rheology in an intraplate deformation. And all my data and analysis comes from analog models. And over here, I show a nice slice or cross-section of one of my models. This is always a nice step when we're doing the models to see a nice cross-section with a lot of deformation or some deformation and really nice displacement at the end of the model. And lastly, I'll be relating my my analysis and results to Ellesmere Island. Excuse me. So what is unique about intraplate deformation, especially on Ellesmere Island? Well, one of the orogenesis on Ellesmere Island is not related to any sort of plate boundaries or subduction zones. And what's interesting is that there is a lot of deformation. It's quite complex in a continental interior setting. And one of the theories that was presented by Calvert was the presence of deep scars, or basically planes of weakness in the deep lithosphere, the mantle lithosphere. And these can be ancient subduction zones, fossil plate boundaries, and so on. And one of the models that was presented by Heron quite nicely, showing how these weak zones can cause deformation in the upper crust by numerical models is over here. He has a weak zone in the mantle lithosphere, and he also has a couple of structures or planes of weakness in the upper crust and the lower crust. And you see quite nicely that it is majority of the deformation is concentrated and initiated because of this weak zone, and it causes a lot of deformation also in the upper crust. But we also know that the deformation or the rheological strength of a lithosphere also controls how it will deform. And so to study this interplay between rheology and structural heterogeneity, we created an experimental design where we tested two parameters. One, the strength of the lithospheric mantle, and then the second, the absence or presence of a weak zone in the mantle lithosphere. So we are only focusing on the deep lithosphere or the lithospheric mantle. This is the experimental box, and this is the indenter that causes the convergence. So all these models are done in a convergent setting. So in total, we have about 4 different setups. We have 2 models that show a nominal lithospheric mantle, and 2 models that have a strong lithospheric mantle. And within these models, there is experiment 1 and experiment 3 that has a pre-existing weak zone. And the weak zone is basically cut into the lithospheric mantle at an angle of 30 degrees. And it is cut across the entire lithospheric mantle, so across the entire length of the box. So to give you an idea of the materials that we use, all the materials that are used are basically a combination of viscous and brittle materials, but we mix these compositions so that all the scaling ratios for thickness, density, and viscosity are the same. And so the models are scaled geometrically, dynamically, and kinematically. For the lithospheric mantle, we use a combination of silicon sand and PDMS. And for the lower crust, we use a combination of bouncy putty, iron filings, and PDMS. PDMS is a silicon-based material, viscous material. All these, the viscous part of the lithosphere is non-Newtonian, and these materials are mixed by hand. They're placed in a form to spread out and to the size of the box, and also to let any air bubbles come out, so that the slabs are completely homogeneous. And then on top of the viscous part of the lithosphere, we sieve a combination of silicon sand and E-spheres. E-spheres are recycled plastic spheres that are hollow on the inside. The scaling for this, for all our models are such that the 10 millimeters in the model is about 25 kilometers in nature. The convergence velocity is such that 0.01 millimeter per second is 10 millimeter or 1 centimeter per year. And 1 hour of the model is equivalent to 9 million years. To give you a more realistic idea of what the model looks like, this here is the Tectonophysics lab at the University of Toronto, where all the analog models are done. This box here is the experimental box with this black device, which is the indenter. And the indenter is pushed by a motor and gear box at a prescribed velocity, which is controlled by this station here. The entire model is recorded by these high temporal and spatial resolution cameras, and this is what our data is based on. These cameras are controlled by this station here. And since our data is based on the experiment or great images from the experiment, only the experimental box is lit up and the rest of the area is kept in the shadows of the experiment. We repeat these experiments several times. As you know, with the analog models, you can have inherent variabilities between the results. So we repeat these experiments several times to make sure that the first order structures that occur between the different experiments are the same and consistent. To get a bit closer look of the box, this is the box here, and this is the indenter. And right now it's filled with glucose syrup, which acts as the asthenosphere. And so the lithosphere with the lithospheric mantle, lower crust, and the upper crust sit on this layer or in this bath of glucose syrup. So this is the data that we get from the images, and the way this here is the velocity field, and the way the velocity field is calculated is from the displacement of markers on the model or in the upper crust, and these markers are basically black sand or sand that is colored black but has the same properties as the upper crust or the rest of the sand. What you see here is a map view. So basically you're looking from above on the model, and it shows velocity in the x direction, so parallel to the convergence direction. The colors indicate the amount of or the actual velocity, and every time you see a break in or a strong change in color, that's where deformation or the formation of a structure and deformation or strain has localized. So here you see the velocity field for experiment 1 and 2. So these are the experiments that have a nominal lithospheric mantle. This experiment here has a weak zone, and this experiment here has no weak zone. In the beginning, you see, so we go from 10% shortening all the way to 30% shortening. In the beginning, you see the formation of a structure. Specifically, it is a fault, and it propagates as convergence continues. It propagates to the end of the box. And eventually, you have the formation of a second structure. In this experiment here that has no weak zone, there is again the formation of a structure that has an undulating sort of pattern on the surface. And then there is a formation of a second structure. They seem to join up and form one long structure that is slightly oblique to the back wall or the indenter wall, sorry. And all the deformation is accommodated by these two structures here. In this experiment that has a weak zone, we can confirm from the cross sections that the weak zone did propagate from, or this, sorry, the weak zone did propagate into the upper crust, and this is the structure that you see initially at 10% shortening. Eventually, another structure forms with an opposite dip direction. However, what's interesting in this model here that has no weak zone, both the structures are actually folds. And and we know this because there is no displacement in the Marco horizon. Both the folds, what is shown on the surface is actually the trace of the fold axial plane. What we also did, because there is a lot of information in the velocity field, what we also did was we created a a map showing the temporal evolution of the model. And we did this by taking a profile across the model, the middle of the model. So basically in the convergence direction. And we took the profile for every time step in the model, and especially since it shows the location of where deformation is or strain is localized, and we stacked them one on top of the other. So this is what, and this gives us a nice display of the temporal evolution of the model. So over here, the y-axis shows the time for every time step, and the x-axis shows the length of the profile. Over here, you see the location of the indenter, and this part here is sort of diffuse deformation of the beginning stages of the experiment. And the moment deformation is concentrated or localized, you see the formation of a fault. So this is what the temporal maps look like for both the first experiment and the second experiment. Again, the experiments that have a nominal lithospheric mantle. Here, the faults that formed, the first fault formed and at some point became less active, and this is when the second fault formed. So both faults are not active simultaneously. In this experiment that has no weak zone, both the folds are active at the same time and simultaneous throughout the rest of the experiment. Here, this is now the strong lithosphere, so the lithosphere that has a strong lithospheric mantle. And in this experiment here, there is a weak zone. And in this experiment here, experiment 4 has no weak zone. Again, you're looking at the velocity field. There is the formation of a structure. In this case, again, it's the fold. And then there is the formation of a second structure, which is a fault. FA relates to the fold axis and F relates to the fault. And then these, throughout the rest of the experiment, these are the only structures that form. Remember, this is the experiment that has a weak zone. In this experiment that has no weak zone, we have the formation of several faults. And as the model continues, there is several faults that form. Some of them are active, some of them become inactive, and overall deformation is distributed across the entire model. These are the cross sections for both the experiments. So here you can clearly see that again, a fault propagated from the weak zone. However, in this model, it is the fold that formed first, and then the fault propagated from the weak zone in the lithospheric mantle. In here, there is several faults that are formed, and we know that these faults formed because of buckling or thickening of the lower crust. So all these yellow arrows indicate thickening of the lower crust, and you can see everywhere that there is thickening, there is a fault that is formed, or a conjugate set of faults that have formed. Again, over here, you can see that in these temporal maps, it shows that in the experiment 3 that has a weak zone, it was first the fold that formed, and then at some point the fault or the weak zone that propagated into the upper crust. And over here, again, you can see that deformation continued with the formation of several faults in the upper crust. Some of them became inactive, and some of them were formed later on, and some of them continued till the end of the experiment. So how does this relate to Ellesmere Island? Well, Ellesmere Island is the structural architecture of Ellesmere Island is quite complex, and it consists of a lot of fold and thrust belts and strike slip faults. But this is mainly because of several episodes of changing or varying plate movements because from the North American plate, Greenland, and Eurasia. As a result, you have the formation of several domains actually, and these domains consist of strike slip faulting and reverse faulting, and again some more strike slip faulting over here. What is interesting is that some of the strike slip faulting over here is one of the first domains of some of the first faults or deformation to form, and this area has also quite similar, shows similar surface expressions like one of our experiments, experiment 2. It has these anastomosing, undulating faults. If you look across a cross-section here, with depth, you can see that the moho and the lower crust is also of varying depth. And this data is taken from geophysical or seismological study. And this sort of indicates that the strength of the lithosphere in this area must also vary. So just to wrap up, in conclusion, the deep structural heterogeneities in the lithospheric mantle do control localization of deformation. But the strength of the lithosphere also influences how strain is translated to the lower crust, and then how it controls the style of deformation in the upper crust. So you can, if you have a completely homogeneous lithosphere, you can have folding. And if you have a strong lithosphere, for example, again, completely homogeneous, you can have distributed deformation across the entire lithosphere in the form of faulting. Note that in these models, we have not taken into consideration temperature because it's not very easy to do in analog models, but this allows us to specifically look at the mechanical aspects of these two parameters only. And despite the omission of temperature dependence, we see quite significant results. Thank you.
All right, thank you, Tasca. You've left us a minute or so for questions. If people have any questions, one popped up here. Phil McCausland, I'll just read you. Phil asks or says, interesting work, thanks Tasca. One feature of your box models is that the faults or folds that develop have a somewhat lobate shape in plan view. That would be 50 to 250 kilometers across. Are there lateral heterogeneities in your model materials localizing this, or is this a product of the vertical components?
Sorry, could you say that again? It sort of broke a little bit.
Oh, I'm sorry. Can you read the question, Tasca?
Yeah,
it might be
I'll
easier.
just stop share here. Okay. A somewhat lobate shape. This would be 50. So I'm guessing you're talking about the model, this second model here. So there are, I'll answer the question for this model if it is it. So there are no heterogeneities laterally. We make sure that there are no heterogeneities laterally. And this here is basically the product of having a completely homogeneous lithosphere. There could be, I show only the velocity in the X direction, but there is very small difference in velocity in the Y direction, and this could be the formation of a strike slip fault. Eventually, this may become a strike slip fault because you notice that these structures are oblique to the indenter. if we were to continue them, if we were to continue the experiment, they very likely would develop into strike-slip faults.
Okay, cool. Thanks, Tasca. I think we have to move on. Just we need to give everybody some time for a break a little bit, but this ends then our lithosphere mantle session. So thanks to all our speakers for today and for the first half of this session in June for showing some excellent new work, a lot of intriguing stuff here. And thanks to attendees for participating in the session as well. So we'll have a approximately 10 minute, less than 10 minute break, I guess now. And we'll start with the solid earth session at 3:05 Eastern time. So wherever that is, you can translate. So about an 8-minute break or so, and then we'll start again. Okay, thank you.
Okay, welcome back everybody now to our second session, afternoon for some, later in the afternoon for others. And this will be the presentations from the general seismology and lithospheric dynamics session. Solid Earth session, sorry. And so first up this afternoon, we have Mamadou Diallo, the role of TDEM, ERT, and GPR forward modeling for survey design and data interpretation. If you want to share your screen and get started, please go ahead.
Hello, everyone. Thank you all for preparing and designing this kind of presentation. My presentation will be a little bit different as what has been made before the beginning of the section. It will concern the role, as he said, the role of the time domain electromagnetic, electrical resistivity tomography, and GPR, ground penetration radar forward modeling for survey design and data interpretation. This work is a part of my PhD under the supervision of the Professor Li Jiancheng from UCAT. The plan of the presentation is I will start with a short introduction of the context of what we are going to present before showing the numerical simulation and how those simulations can help survey design strategy. And again, in the third part, in the impact of the numerical simulation for interpreting the data before presenting the conclusion of the presentation. We are living in a context of growing demand for mineral resources, and for surface shallow mineral resources are vanishing. So, for example, in Canada, if we take the last 2 years and this year, we can see here how is increasing the investment in mineral exploration. Even because of the pandemic, we still have some growth in the exploration. For example, if we take the three big mineral provinces in Canada and British Columbia, Quebec, and Ontario, we have a very good increased investment in mineral exploration. So for responding to that demand, we need to go find some deep mineral resources because of the importance of the demand. How can we reach those deep? Is like, first we can do some innovation in the method of exploration, or we can return back to the old sat mine and then start with the new strategy for deep exploration in that. So we need to find out how those infrastructure are. The old gallery advantage and issue for the surface infrastructure, they can be a problem of stability because of those older infrastructure. And if they are unknown location, they can create a security problem for the future exploitation operation, like the reopening. And these gallery, they can be empty or like void and filled with backfill or water. That water can be fresh or contaminated. So it can create some environmental issue in the process of dewatering the other infrastructure. But if we know them, we look at them, they will be usable for reopening old mine and help reducing the cost of future exploitation. The quick questions for us, what can we do to increase the deep of mineral exploration, and what can we use geophysical method to explore this infrastructure? For that, we will present a numerical simulation and to show with these three geophysical methods and see how they can impact the field work. And when we go from Maxwell equation is the interaction of the magnetic and electric field and the constitutive relationship that make those fields, the relationship between the fields, those fields and the physical property of the material, we can have this wave equation that describe the electromagnetic wave in terms of electric field. This term is the diffusive term of electromagnetic. In low frequency, we can have the principle of time domain electromagnetic. We have a transmitter, it generates a primary magnetic field, which one in the presence of conductor will create an eddy current, and this eddy current will create a secondary magnetic field. This we record here. On the second term, the most important parameter property is the conductivity, because we need this conductor to be very conductive. And the second one is the wave propagation in high frequency. We can analyze in seismic, we can have a reflection mode in the interaction between two different material, or we can use the transmitting mode like in tomography. And the physical property is the electric constant of the material, the conductivity, which one is very important here. And for those simulations, we suppose that the magnetic permeability, the material are not magnetic. And here for the ELT, the electrical is based on the Ohm law, in which the potential equals the resistance by the current. And the principle is we have used for electrode and 2 injection electrode and 2 potential electrode. And writing the Ohm law here, we can have the resistivity of the underground material by this formula. And many configurations are used in the technology, where the most of them knows at Venel and Schlumberger, and each configuration has a geometrical factor here that we use in the formula. And because of we are going to talk about modeling, is here in geophysics, when we go from the geological model, if we go from there and we use for when we talk about forward modeling, And we have a setup like TX and RX configuration. And when we model this, we can have a forward modeling result. And if we consider this is a measurement, field measurement, we can go back to the geological model by the inverse problem. And this is initial model, we use an initial model and we choose an inverse method and then to go back to the geological model. When we are modeling, we need to define the dimension of our setup. For we can have 1D, 2D, and 3D. For us, we're gonna use the 2D for the GPR simulation and 3D for the ERT and time domain. And the geological model, we need to be discretized. And for 3D, we can use cubic element here, for example, hexaedron if we have topography, or if we have many shared factorial block. 3D, we can use the tetrahedron. For us, we will use the cubic one. And the example of the model for time domain electromagnetic simulation, we create this model for near the boundary, we had a cross mesh, and where we put the gallery, we put some fine meshes. And here, when we make the zoom, we can have, we put a gallery here with the length of 200 meters and the cross section 6 by 6 meters. The simulation for the ERT we made was done by ERT Lab Studio that can help us where we have this kind of configuration here with 9 line, 360 electrode. And when we have the spacing between electrode is 10 meter and the lines 10 meter. We create a model with a background resistivity of 5,000 ohm meter here. And the cell size in each direction is 5 meter. We can see here the result of this simulation is because of only the background. We don't have anomaly, we just have a smooth model, but we can notice here the impact, the influence of the electrode, the artifact created by the electrode on the ground. And here, when we put in this model a gallery, high resistive gallery here, this 1,000,000 ohm meter at different depths, we can see the result here at 75 meter with east-west gallery, and here 100 meter. And we have 2 gallery east-west, but at different level, and they are parallel to the survey lines. And the last one is we put 2 gallery at the same level, but perpendicular to the survey line. The simulation was able to see them too. That will help us to know how if we know exactly what we are expecting, we can choose the way to put our setup. For the time domain electromagnetic, we use the Loki code, which is included in the Maxwell for electromagnetic geophysical processing. And then we use this configuration with 9 transmitter here, and then 12 boreholes. We have 50 meter between 2 boreholes. And we have 3 boreholes inside of the gallery. For the model, we use the host material will be 10,000 ohm meter. As we said, we have the gallery can be empty, donc high resistive, and filled with fresh water. So that's when we use this resistivity 50, and it can be acid water because of the acid mining drainage. Like we use 2 panels of the resistivity 5 and 10 ohm meter. When we simulate the TX1 and all the borehole here, I have the result for the borehole 1 with the acid water 10 ohm meter. We can see the gallery was put at 600 meter down, so we can find the effect of the gallery in the 3 component of the electromagnetic field here. And so what we can see the effect of the gallery. And here I present the lateral distance detection of the gallery. For example, if I take the borehole 1, borehole 2, which are 50 meters away from each other, we can see the result. For the borehole 1 was able to see the gallery, and then after that, the secondary magnetic field tried to vanish. So it was very, in the noisy media, it's not guaranteed to see it at 100 meters. So we can say, okay, our lateral detection will be near less than 100 meters. And here because of the many material we can have here, we change because of we vary the resistivity of the gallery, and we take the result for the borehole 1 because the electromagnetic for conductive material, the void is resistive, so we don't need this one. And then here for the freshwater, we have a small signal here that defines the gallery, the presence of the gallery. And for those two, we have an intense increase of the effect of the gallery. And here, the effect of the TX location. We have the, just to remember, we have the 9 TX, TX1 to TX3 at the north, and TX7 to TX9 at south. And in the middle, in the center, we have TX4 to TX6. What we can observe here, the transmitter located at the north and the south was able to see the gallery because of they give good coupling between the primary field generated by the transmitter and the conductive gallery on the ground. But for those 3 in the middle, we have like bad coupling between the TX and the gallery, so they wasn't able to help us see the gallery. So this will help us to do where to put our transmitter to be based on the investigated error. And for the GPR here, with the ground penetration radar, we use a code based on the Irving and Knife with 2D in MATLAB to simulate. Our setup was something like that for simulating 3 gallery. We have the first one was filled with air, and the second one water and the backfill material. And the physical property here, we can find the conductivity very important for the GPR because it's influenced a lot the wave. And then for the here it was 0, and then here 0.5, and we have a 0.001. And the electrical constant of the material, we have 2 poles, like for air it was 1, and then for water is 80. Donc they have a good contrast between them. And the frequency used here, it was 100 megahertz because we have 2 boreholes located at 5 and 10 meters. We use a large time window for the borehole to give the time the wave to come back to the receiver. And the cell size was 10 centimeters, it was very small. The result for the borehole 1 and borehole 2, we have that here. And then we can notice here the top of the gallery here. And then here we have the bottom of the gallery. And we have, even if it's late here, we was able to see it, but here we have some kind of interference, and maybe it's related to the conductivity of the material is because the Highgate conductivity was here. And for this one, we have a flat and then late because we give 250 nanoseconds, and the borehole was very far from the from the galleries. The survey design strategy, as what we can see here, the resistivity can give us a large area coverage, even if the resolution will be low for deep survey, and identify large panel of gallery contrast, resistivity contrast. And the step 2, we recommend to use the time domain measurement with the surface to borehole configuration because it gives us a very deep survey. And but even if we have small error around the borehole was covered, and only for the gallery with conductive material. And the measurement in the borehole located near in the area identified as gallery location with the ERT. So based on that, we can do that. And for the step 3, we can do some GPR reflection mode, use the borehole very close to the identified zone by those 2 methods. And based on the geological information, choose the adapted frequency to actually go the depth and the resolution compromise. For example, here, I increase the conductivity of the material to see how it's gonna impact, and we almost lost the signal of the 3 gallery, even if we were able to see it a little bit here, some impact. And for data interpretation, for the resistivity of the gallery, I use a background of about 10,000 ohm meter, and I vary the resistivity of the gallery to high resistive to low resistive value, to low resistive gallery. And we can see here it was able to identify them, high and the lowest one. But when the resistivity is close to the background resistivity, the signal was very small. And here, the field variation over the fourth direction, when the borehole is located at the south and the north, the signal was strange, and because of the contact surface between the primary field and the gallery. For those two, we have in the direction east because of the small section of the gallery. So the response of the gallery was very small. And how we can interpret this one too very easily is like we have here our tree gallery with their parameter, and the top of the gallery can be seen here, and the bottom of the gallery, we have it here. And we have two triangles here that represent three patterns because of the material of represented in the gallery. As conclusion, we can say the combination of the three geophysical method of forward modeling helped to outcast a strategy for shallow and deep underground oil gallery detection. And the ERT method can offer very large survey area for identifying zones with high density gallery. The time domain increase the depth of the survey area than the other two techniques. And with the GPR, finally, it will be possible to extract the information about the material filling the gallery because of the high resolution of the measurement and its sensitivity to a large type of material. Thank you. Other questions?
Great, thank you very much. There's no questions currently in the Q&A, but if anyone has a question, we've got time for one, possibly two. I'll just give folks a moment to type and ask. So with the, oh, here we go, from a question from Sam. Did you consider surface to borehole or borehole to borehole resistivity?
For the resistivity method, it was only surface there because we will use some electrode on the surface, the configuration here. We put all the electrode on the surface for the resistivity.
And we have time for one more question if anyone has one. Otherwise, we'll say thank you very much for a great presentation, and we'll prepare for the next one to start here. Thank you. Okay, and next up, we'll have Ian Lumb talking about growth and decay asymmetry in Earth's axial dipole field as a criterion for modeling the geodynamo. And I can see the slides are up and ready. So if you take it away as you like here, Ian.
Great, thank you very much, Andrew, appreciate that. So as Andrew says, I want to focus in on some work that Keith Aldridge and I have been doing at York University regarding use of paleomagnetic data currently, but with some interesting upside, to gain some insight into what's going on inside of the Earth, and in particular with respect to the geodynamo. So I'll spend a little bit of time speaking about the data itself. I'll then make a bit of a transition and talk about how we can infer various characteristics, particularly about processes when it comes to the geodynamo. And that'll allow me to then frame up the ability to talk about some work that Keith has been championing for some time now in looking at how a different way, a different means of exciting the geodynamo can be thought of and can produce some interesting results, and we'll summarize where we're at. The place I wanted to start was with a relatively recent review article. I do apologize, this is a very busy slide. I've highlighted in red the parts that are most relevant to the presentation. So this is from a review article by Vallée and Fournier, 2016. And they were looking specifically at geomagnetic reversals, and their emphasis was primarily paleomagnetic data, although they did also speak about some data from a related data set that I'll allude to later on in the presentation. And of course, some of these points here, I think, are going to be fairly well known to the community. The fact that when there is a transition, that the field, particularly the dipole component of the field, changes its intensity rather dramatically, decreases rather dramatically. Quite often during these phases, the field becomes decidedly non-dipole in nature. There can be quadrupole moments that become quite significant. We're going to be leveraging data that is captured the magnetic field through time, through sedimentation and through volcanic formations of one kind or another. And this allows us to get some insight into the variation of the magnetic field over time. But the point here at the very end is the one that I'm most interested in. This is the asymmetry that is alluded to in the title. And to be more precise about that asymmetry, you can see it over here on the right. This was actually, this is a figure from Valet et al. In 2005 that really started speaking about this asymmetry in a real sense. You can see that what they've done here, they have a number of events. The most recent, the Brunis Matayama that's an example, of course, of a reversal. And you can see that the consistency, when you take each of these events from the paleo intensity data and you sort of normalize them to some reference point, as you can see here, roughly speaking, the lowest value of the virtually averaged axial dipole moment. You can see that there is a fair bit of consistency here, and you can also see that there's a fairly pronounced asymmetry. The growth rate of the field is different from the decay rate. Now, it's not as if this is a completely closed problem. There are other considerations that the paleomagnetists themselves are looking at. So there are some, there is some additional work to be done there. What they find particularly complicating is the fact that during a reversal, the field does not exhibit a nice monotonic decline or return. There are oscillations that are present. And there's actually been some work, it's not actually referenced on this slide here. Most of the points here are from Valet and Fournier once again. There have been additional studies that have suggested that even when the field is not experiencing some kind of a transitional behavior, when it's not reversing or experiencing an excursion, there is still evidence that the field is asymmetric. And a lot of the work that is in the literature tends to associate processes in fairly broad terms with the behavior to try and account for this asymmetry. And this is something that Keith and I are particularly interested in. So here are some examples from a relatively recent paper by Simon et al. And what you can see, there are several different data sets that are shown here. The traditional paleomagnetic data, which is obtained from various stacked records. That's an important point. The paleo intensity results that have been analyzed, they're not from a single site, not a single, for example, some of the early work of course was, but these days it's very common to use so-called stacked records. So the records are actually compilations that have been put together from a number of different locations. And so one example of such a stack, which is almost so faded out here, you can barely see it, is the Piezo 1500 data set, which is kind of shown in this sort of bluish gray tone here. And superimposed on this in more of the reddish hues is some very interesting data. And this comes from basically beryllium isotope anomalies. So when the main dipole component of the field decreases during one of these magnetic events, it affects the ratio of beryllium-10 to beryllium-9. And as a consequence, there have been a number of studies where this data has actually been extracted. And very importantly, this is considered a completely independent data set from the traditional paleomagnetic data. And yet the consistency between the two sets of data, you can see here that the beryllium data gives the notion of a beryllium dipole moment. It's rather striking. So over here on the left, we have the relatively speaking recent Lumb excursion. And over here on the extreme right, we have again the MBT reversal and another event in the middle here. Now, what's quite interesting is to start looking at with data available from several different sources now, independent sources. In fact, one of the striking contributions of the beryllium data sets is in certain cases, particularly the Lumb excursion case, the resolution and time of this data is quite good. I think some of the best stuff is on the order of about 200 years, and so we can start to really analyze these transitional periods and try and extract information from them. So this is a figure taken from a recent paper by Gortz et al. And as you can see here, they're looking again at basically the axial dipole moment of Earth's magnetic field on the virtual axis, time on the horizontal axis. Now, you'll notice that they've got this should probably be labeled age rather than time, as the present is on the left and the past is on the right, as seems to be the convention here. The point of the slide, however, is that these particular authors are, amongst ourselves, also very interested in these transitional phases. And so they are similarly interested in estimating decay and growth times. This should probably be considered a growth given the orientation of time here. And they're also interested in quantifying how long events take place. Now, if you spend any time with paleointensity or beryllium isotope data, you'll know that that's a bit of a challenge. That's something that our group is rather familiar with. So there is a degree of challenge that's associated with that. But these two parameters, so the decay time as deduced from observational records and the duration of events, so how long one of these transitional events takes. Think of how long it takes for a reversal or an excursion to occur. These are two parameters that Gortz et al. Zeroed in on to characterize reversals. And they ended up providing this plot here, which particularly struck our interest. You can see that what they've done is they've plotted the average decay time on the vertical axis and the event duration time over here on the horizontal axis. Now, the data here is worth speaking about. The two data points that are down here towards the bottom of the figure, those are actually, as you can see from the legend here, those are results from standard paleomagnetically obtained paleointensity, relative paleointensity time series. So the so-called SINT 2000 stack and the PATM 2M stack that are, both really quite well known, quite often utilized, cited in the literature and so on. So if you take this data and you deduce the average decay time and the average event duration, you get data that plots down around here. So what was particularly interesting about this plot from Gortz et al. Is they also considered results from simulations. And the most interesting, I think, are the results from a simulation here that's just modestly labeled 3D. And I was clearly pointing at the wrong data. My goodness, the PATM data in this, that's terrible. Apparently I've developed color blindness or something. So the observational results plot up here towards the, actually I've got a click through here that tries to make this point. The observational results plot up here towards the top. The results from a three-dimensional thermochemical dynamo simulation that is referred to and detailed in the paper is plots way down here at the bottom. The other results here are obtained from various simplified versions of dynamo models for our planet, low dimensional models, models that are in one sense or another analog. So even though this this model here called G12 looks you know, kind of interesting in that it's in the sort of the right neighborhood of the observations, we can't really put too much emphasis on that. So obviously not a lot of data points yet, and that's really one of the points I want to make from the presentation, is that there's a need for additional data points. But clearly there's this quite significant difference here, and we think that this is a difference that's quite important as it relates back to processes that are going on within the interior of the planet. So there's a bit of a gap here between the observations, which are right here, once again, and most of the simulation results, which are farther down the slide there. Now, my colleague, my co-author, Keith Aldridge, has been looking at this, this data and this problem for quite some time. In fact, together with Ross Baker, back in 2003, they published what we believe is the first attempt to look at this paleo intensity data and to extract growth and decay rates from that data. The initial work looked at results, I believe, from just a single location. They subsequently have applied their methodology to these stacks of data. They developed an automated scheme for choosing the intervals that describe the relative transitions of the magnetic field. And so this is a representative illustration of how they would obtain growths and decays from, in this case, the Padam stack, and for the Brunas-Matayama reversal. You can see over here on the left, again, notice the orientation for time. So the present is actually somewhere, you know, way over on the left there. And so the red slope here, we're looking actually at the log of the relative paleo intensity data. They've been applying that approach for quite some time. So the log of the relative paleo intensity data is shown through by the red slope here, and you can see the value that's estimated, and then the decay by the slope that's indicated in blue. There is a very nice theoretical result that derives from some work that Kurzweil did. We're very interested in a particular kind of a problem here, as you'll see from the next slide. And the conclusion from that theoretical work is that if you subtract the decay rate from the growth rate, you actually obtain a sense for the strain. And the strain in this case is a mechanically generated strain that is generated by the lunar solar tide. This particular strain gives rise to what is called an elliptic instability. The motivation for this work, as you can see from this slide here, is that there was a significant amount of work done in Keith Aldridge's hydrodynamics lab. And in fact, the next speaker is, he'll see this stuff as being very familiar, as he was very involved in this. I'm referring to Behnam Seyed-Mahmoud. The point of this is to just illustrate that in a rotating fluid that is in some sense an analog for our fluid outer core, it's quite possible and quite relatively easy to excite the so-called elliptic instability. So what Keith and another colleague, David McMillan, have done is they've used the strain rates they have that have been obtained from the paleo intensity data to calculate. They have calculated the strain rates from the growths and decays in paleo intensity data, and they find a rather interesting correlation between the value of the strain rate and the various behaviors, the various transitions of the magnetic field. It turns out that these strain rates that are deduced from the paleo intensity observations also align rather well with theory. And I'm going to kind of go over this a little bit quickly as I'm looking at my time. So what I think this tells us is that it's a very interesting time to be characterizing reversals from observations. We have both relative paleointensity data, which is obviously we've been working with for a very long time. The beryllium isotope data is extremely interesting and starting to become increasingly available. So we can actually go beyond just looking at the average event durations and the average event times. And we need to because of that divide. It's pretty clear that the observations and the work from the various kinds of simulations, particularly based on traditional models for the geodynamo based on thermochemical convection, just aren't quite lining up, and certainly lends the possibility for there being other mechanisms that could be at play. So we are going to be introducing a third dimension to account for growth, something that was neglected in the Gortz model, and then continuing to scour the literature, to collaborate, and quite likely to develop our own models that favor elliptic instability as a different means for introducing some kind of a means for developing a geodynamo. There's also additional upside, so to speak. Excursions are also extremely interesting, even though they don't represent complete changes in polarity of the magnetic field. There's still a tremendous amount of data that is available there. And because some of them are relatively speaking recent, and they're available with data from a multiplicity of sources, it's quite interesting to consider that possibility too. So I've been talking about some nuances, perhaps. I'm referring, of course, to the growths and decays in relative paleointensity and beryllium isotope data, and the possibility for using those nuances, the asymmetry between growths and decays, to try and deduce a little bit more information about what might be going on in the inside of our planet. We have been for quite a long time, this is an effort championed by Keith Aldridge and collaborators, have been favoring the idea of applying a model based on elliptic instability to the interior of the planet. And I should say there's a tremendous amount of interest in general in turbulence and in mechanically generated turbulence as a means for driving convection in the outer core, as a possibility for generating the geodynamo these days. Some of the preliminary work indicates that there's a nice looking correlation between reversals and maximum tidal strain rates, and that those rates line up with theory quite well. And there are a number of different priorities that I think bear further research, as we say, to help reduce some of the ambiguities in these estimates, and of course put some more data points on that plot from Gortz et al. And looks like I almost managed to finish on time.
Thank you very much, Ian. I'm afraid that we are right at our time window. There is a question from Julian here that perhaps, oh, okay, we can take one question. So let's take Julian's question. Hopefully I can read it quickly. Ian, you alluded to hypotheses referencing the impact of the mantle's thermal field on reversals and some theories about paths and asymmetry. If I understand correctly, is there any similar thinking regarding magnetic or compositional asymmetry or anisotropy of the magnetic properties of the inner core? Do lunar tides affect inner core growth?
Wow, that's a very interesting question, and I will just have to take that one offline, as it's not something I've really spent any time with, but I do appreciate the question.
Okay, great. Thanks very much. Fiona, did you want to introduce the last?
Certainly, yes.
Sure.
So our final talk this afternoon is going to be given by Behnam Seyed-Mahmoud, and the subject is the free inner core nutation. So I'd like to invite him to share his screen and kick off the presentation. Behnam, are you there?
Yes, I'm here. I'm just looking for my file.
Okay, perfect.
Just 1 second. I think I found it. Yes.
Great, thanks very much.
Thank you. Let me just. Okay. My work is in my research is in the dynamics of mostly in the dynamics of the liquid core. And to that end, I also study the, let me just, sorry, this is, I need to go back to the beginning. I'm right at the end here. Okay, so this is the, okay, this is, so I also study the Earth's wobble and nutation. This is the outline of the talk. The Earth's wobble modes, the ones that we know of, are Chandler wobble, which is the modified Eulerian wobble. That is the Eulerian wobble with the body which also has a liquid core. Free core nutation. Free core nutation is actually the inertial mode, spin-over mode. The core dynamicists are familiar with spin-over mode. This is also is the same mode, except that, of course, it's when the Earth is wobbling. Tilt-over mode. This is just the mode for any rotating body. Sometimes it's sort of confused with spin-over mode. We just had a paper out in 2021, which tries to distinguish between the two, to give the distinctions between the two. Inner core wobble and free inner core mutations. These are associated with the inner core, and that's the topic of my talk today. Inner core wobble has never been observed, and Matthews et al. 2002 claimed that they had observed free inner core nutation, but that has not been observed, confirmed. Now, during the free core nutation, the motion in the core is almost purely toroidal. We showed in 2021 that during the Chandler wobble, the motion is nearly geostrophic. That is, the frequency of the mode is very small, and it's almost as if the motion is solid body rotation. These two parameters that I've introduced here, we will look at later on. They become important. I just wanted to emphasize that the moment of inertia of the inner core compared to that of mantle is actually very small. It's almost comparable to the ellipticity, dynamical ellipticity of the liquid core or the Earth in general. In 2017, we showed that if we consider the motion of the liquid core, if we don't truncate in the theta direction, the spherical harmonics, if we don't truncate them too quickly, we'll see that the period of the free inner core nutation actually never converges. It fluctuates as you increase the number of terms, it fluctuates about a mean. Previously, and even now, people truncate these at this level, which gives you about 753 days. So to study these modes theoretically, to predict these modes, it is common to introduce wobbling motion at each major segment of the Earth. So 1, 2, 3 refer to inner core, liquid core, and mantle. And each one of these are assigned a wobbling term. So a non-uniform term. And you will see that today I will refer to Matthews et al. 1991 quite a bit, because they and Davry and Var, they were the first, well, that I know of anyway, that introduced, that used these in conservation of angular momentum to study these modes, and also they predicted the existence of, or they proved kind of the existence of the FICN, the free inner core nutation. They used Sassau's approximation. I will talk about it a little bit more later. But today I will show that introducing this M2 is really unnecessary. The first part of my talk is about that. That's really unnecessary. It doesn't do anything. And then later I will show that their results, the results that they have got, is actually equivalent to setting this M3 to 0.2, so that the mantle also rotates. Their approximation implies that mantle is also rotates uniformly. Okay, so this is a graphic representation here. Omega-1 is the rotation rate of the inner core. Omega-2 is rotation rate of the mantle, liquid core, and omega-3 is the mantle, that of the mantle. I use a uniformly rotating reference frame. Okay, so I write all of these, the motion in this reference frame. Many people use this reference frame, but reference frame is only a tool. So I use a uniformly rotating reference frame. So I want to show that, well, I mean, the dynamics in of the liquid core is already very complicated. And by introducing M2, of course, we make it, I will show that we make it much more complicated than it should be. And again, I will show that that's not really necessary. Now, velocity of the mass element in each segment of the Earth is like so. I'm considering here a rigid inner core and rigid mantle and a liquid core. But as I mentioned already, the liquid core also usually is assigned a rigid rotation plus a deformation. So because we are dealing with oscillations, then these all the dynamical terms are separated as the spatial and oscillatory components as such. And that's usual, that's common. Now the displacements, we deal with displacements. So the displacements in the inner core, liquid core, and the mantle are given as such. Again, they have in the inner core and mantle, it's just rigid rotation. And in the liquid core, we also have a deformation component. The equations of motion, this is the incompressibility condition. I consider an incompressible liquid core. And this is, of course, Newton's second law. Okay, so force is equal to the mass times acceleration. We divided it by rho, so acceleration is equal to the field here. And chi is pressure, reduced pressure. So if we write it in terms of displacement, then those equations, of course, now you can see that we have these terms M2 in the liquid core. So if M2 is 0, you can see that the problem becomes much simpler, which is already a complicated problem. And if we if we do some steps to calculate U, you can see that the displacement in the liquid core becomes like so. It also depends on the rigid rotation component, of course. Gamma P is like so, and the sigma is just a non-dimensional frequency. I divided omega by 2 omega. And if we use divergence of U here, that gives us the Poincare equation. So Poincare equation already doesn't depend on M2 anyway, because the divergence of this term is 0. Okay. First, let's look at the boundary conditions. K again is either 1 or 3. Q2 is already the displacement in the liquid core. If I apply the boundary conditions here, this is U, of course, n dot U. If I apply the boundary conditions, I show that the boundary conditions, both at the inner core boundary and core mantle boundary, don't depend on M2. So you can see that they disappear. M2 disappears from the boundary conditions. It already, the boundary conditions don't depend on the rigid rotation component in the liquid core. Okay, again, this is representation of U displacement in the liquid core. To solve the problem, so we have boundary conditions. To solve for the modes, we also need the conservation of angular momentum. Now, each component has a rigid rotation component. Okay, so HK here is only the rigid component. It's angular momentum due to rigid rotation, omega mk. Okay, so if I take the derivative, I will get this. Now, each component, of course, if they were rigid and they were independent, you would set this to 0 because it's free oscillations. So Vk for each component, if they were independent, it would be 0. You can see that we will get tilt over mode, and we would get the Eulerian wobble. Now, of course, for the Earth, we need to add these 3 plus the component that is due to the displacement in the liquid core. So the component of H due to liquid core becomes like so. As I showed here, U depends on chi and on M2. So here you can see that it has an H angular momentum due to chi and angular momentum due to M2. Now, if I add these 3, K1, 2, 3, and this one, you can see that this component cancels the component due to rigid rotation in the liquid core. So you can see that the angular momentum also doesn't depend on M2. So basically, we don't need to attach a wobbling components to the liquid core. It doesn't do anything. Now, just the next part of the presentation deals with computing the periods of inner core wobble and free inner core nutation using what has been used. I mean, using Matthew et al. And others approximations. This is the angular momentum of the inner core, and these are the torque exerted on the inner core. So the derivative of angular momentum, right, which is equal to the torque, of course. So in 2017, we showed that the torque on the inner core, gamma 1 and omega 1, pi 1, which are the gravitational torque and the pressure torque, are given as such. In 2021, we showed that we use a different mean to show that if we use Sassau's approximation, that's equivalent to setting alpha 3. That means the wobbling motion of the mantle to 0. So I followed that lead and set alpha 3 to 0 in the torque on the inner core. So alpha 3, I set it to 0 here and here on the gravitational torque and the pressure torque on the inner core. Now, Sassau's approximation, if we use the description that I explained, omega 2, then Sassau's approximation says that dH2 by dt minus omega 2 times cross H2 is equal to approximately 0. Now, if Matthews et al. Extended Sassau's approximation and said that this chi on the inner core in the torque is also 0. So I set that to 0 too. I use their approach. So if we do that, then the torque on the inner core is the, of course, derivative of the angular momentum. We get this equation. I do some, I introduce some terms here, which are done by Matthews et al. And also by Rochester and Crossley. If I do that, remember that I set alpha 3 to 0 and also pressure on the torque to 0. I get exactly what Matthews et al. Get here. And also for omega of the inner core wobble. So this is the counterpart of Chandler wobble for inner core. Remember that inner core is not free to, it's subjected to torque. But I also get this frequency, which is identical again to equation 29 of Matthews et al., except for this term. This is what I introduced at the beginning, that the terms of order of E1A1 divided by A3. So that's 10 to the power minus 8. It's a smaller than square of ellipticity. So it's smaller than second order terms in ellipticity. Remember that here I only consider first order terms in ellipticity. Okay, so I get identical results for free inner core nutation. Okay, now if you use the angular momentum conservation, okay, then of course we get this equation for angular momentum conservation. So we need another equation, which usually we use boundary conditions, right? So on the inner, if the mantle is rotating uniformly, then you can see that at the core mantle boundary, the deformation term, of course, is equal to 0. The n dot u is equal to 0. But on the inner core boundary, then we have this term. We cannot find a smooth solution for chi, which satisfies these two at the inner core boundary and core mantle boundary. The reason for that is because the problem is ill-posed. So this is again from Roger Say and Seyed-Mahmoud 2001. You can see that this is, remember that for Chandler wobble, the motion is very small. The frequency is of first order in the ellipticity. And I will show, actually, why not show it right now? You can see that we have a square of frequency here. So this term is very small. So that becomes, for Chandler wobble, it becomes like so. Okay, so these are, and you can see the characteristic equations in the free core nutation. Okay, now the conclusion here that is that we need a more rigorous description of the inner core dynamics to compute the free inner core nutation. Okay. My time is up, so thank you.
Okay, thank you very much for your presentation. I think we are probably out of time for questions unless somebody has a really burning quick question. I'll keep an eye on the Q&A box, but in the meantime, I'll just give you a couple of notices while we're waiting to see if there's any more questions. First of all, of course, big thank you to all the authors this afternoon, all of our speakers, to the conveners and co-conveners, and of course to all of the audience members for attendance and participation. I'd like to remind you that after this session ends, there'll be a short break. The current webinar will close, but please come back using the same Zoom link for our CGU Solid Earth Annual General Meeting, starting at 4:20 p.m. Eastern, and of course everybody is very welcome to attend. And on a similar note, we have, as a reminder, we have our final CGU summer session next Tuesday, that's July the 20th, starting at 1:20 Eastern Time. And in that session, we'll have the first 3 talks being our Chevron Award candidates in seismology. And that will be followed by 5 talks on geophysics and hydrology in high latitude and high altitude environments. And then following that series of talks, you're all invited to attend the union-wide CGU annual general meeting, and that starts at 4 p.m. Eastern. So just a quick look. I don't see any questions in the Q&A box. So again, thank you very much to the presentation, for the presentations. So thanks again for everyone's participation, and I hope to see you in a few minutes for the Solid Earth AGM. Thanks a lot.